Hi everyone, and welcome to some more calculus, more relative max and min exercises. We have a function here, and we want to determine the intervals over which f of x is increasing and decreasing. And we want to identify all relative maximums and minimums. Here's our function. And one of the reasons we're doing more relative maximum, relative minimum exercises is that so far in our examples, all of our relative maximums and minimums have occurred at type A critical numbers. That's not always the case. Sometimes we have relative maxes and relative mins at type B critical numbers. Sometimes we have functions that have relative maxes and mins at both type A and type B critical numbers. So this is an exercise that we should see. We're looking to see where the function's increasing and decreasing. So again, the first thing to do is to compute the derivative and find the critical numbers. See, 9/5 minus 5/5 is 4/5. And 4/5 times 9 is 36/5. 4/5 minus 1 is negative 1/5. Okay, here's our derivative. Now, if I were just doing an exercise on a test where it told me to compute the derivative of this function, I'd stop right here and go to the next exercise. But what I need to do is find the critical numbers, which means that I'm going to have to work with this expression. I'm going to have to set it equal to 0 and find the value of x that makes this function 0. And I'm going to have to find the x values that cause division by 0. So I might as well simplify it right now and just get it in a form that I'm comfortable working with, so that then I can set this thing equal to 0 and find the type A critical numbers, and so that I can look at this thing and find any values of x that cause division by 0. So I'm going to continue to rewrite this until I feel like I have it in a form that I can work with easily in an algebraic way. So let's see, I have a denominator here, I have a denominator here, so I think what I'll do is put 5 in the denominator. I'll have 9x to the 4/5 over 5 minus 36. And this is a negative exponent, which means I can put x to the 1/5 in the denominator, and the exponent will be positive. So I have 5, and I have x to the 1/5 in the denominator. Okay, looks good. I'd like to combine these two terms into one term. I need a common denominator. Both denominators have a factor of 5. This one also has a factor of x to the 1/5. So I need to give this term a factor of x to the 1/5 in the denominator. And I do that by multiplying top and bottom by x to the 1/5. Whoops. In the denominator, I'll have 5x to the 1/5. And in the numerator, let's see, I have x to the 4/5 times x to the 1/5. What do the exponents do? They add, don't they? 4/5 plus 1/5 is just 1. So this becomes 9x minus 36 over 5x to the 1/5. Okay, I like this form. I think I can work with this algebraically. So, I guess I'll erase some of this. And I've just discovered that in simplified form, the derivative is 9x minus 36 over 5x to the 1/5. And I need to find the critical numbers. Now think about this. What is the identifying characteristic of a type A critical number? Doesn't a type A critical number make the derivative equal to 0? So that's it. F prime of C equals 0. So we set the derivative equal to 0. And we see what that forces x to be. Now, I guess there are a couple of ways of doing this. We might be hesitant to multiply both sides by 5x to the 1/5. In general, it's not a good idea to multiply or divide both sides by a factor that has a variable in it. In this case, it won't hurt, but let's approach this from a different perspective. We have a quotient or a fraction that's equal to 0. What's the only way that a quotient or a fraction can be equal to 0? Isn't it when the numerator is equal to 0? So the only way this whole thing can be equal to 0 is if the numerator is 0. So this means that we have 9x minus 36 equal to 0, and 9x equals 36. So we have a type A critical number, x equal 4. Now we need to look for type B. And what is the identifying characteristic of a type B critical number? Isn't it that it causes division by 0 or it makes the derivative undefined? Here's our derivative. We're going to have division by 0 when 5x to the 1/5 is 0. So let's see. F prime of C is undefined. That's the defining characteristic of a type B critical number. And 5x to the 1/5 equals 0 causes division by 0. And that means x to the 1/5 is 0. Now, what number, when we multiply it by itself 5 times, gives us 0? 0, right? If we don't look at it that way, we can just raise both sides to the 5th power. And that will give us x equals 0 to the 5th. We get x equals 0 as a type B critical number. Looking good. Okay. Let's put all of our information together here. Let's see, x equals 0 are the critical numbers. Step 2, draw a sign graph of the derivative using the critical numbers to partition the x-axis. And 3, choose a test value from each interval to plug into the derivative. Okay, so here's our derivative. Zero is a critical number. 4 is a critical number. And from each interval, we pick a test value. Now, I guess there are a couple of ways to do this here. One thing we can do is recognize that the 5th root of a positive number is positive, and the 5th root of a negative number is negative. In that way, we don't really have to compute the 5th root of a value. The other way is just to pick numbers whose 5th roots we know. So let's see, 1's a good test value. The 5th root of 1 is 1, so that's a good value. Plug in 1, we get 9 minus 36 is negative 25. Plug in 1 here, we get 5. Negative 25 over 5 is negative 5. When x is 1, the derivative is negative. So it's going to be negative throughout this interval. Okay, over here, I guess I can pick a test value that has a cube root that I know. 8 is a perfect, whoops, not a cube root, a 5th root. Holy moly. You know what? Well, 32 is a perfect cube. Now, I'm going to have to compute 9 times 32. I don't want to do that. I'm just going to pick 5 as a test value and use the fact that the 5th root of a positive number is positive, the 5th root of a negative number is negative. So I take 5 and plug it in here, and I get a positive number on the bottom, and I get 9 times 5 is 45 minus 36, which is 9. I get positive over positive, that's positive. At x equal 5, the derivative is positive, so the derivative is positive throughout this interval. And now we go over here. -1's a good test point. We can do this one of two ways. We can say this is negative and the fifth root of a negative number is negative. Or we can say, hey, I know the fifth root of -1. It's -1. Either way, the bottom is negative. And when we plug 1 into the top, we get -9 minus 36 is -45. We get negative over negative positive. When x is -1, the derivative is positive. So it's positive throughout this interval. And that tells us a lot. We've pretty much got half of the exercise whipped. So let's see, f of x is increasing on the intervals and from -infinity to x equals 0, the derivative's positive, so it's increasing on this interval. -infinity to 0. And from x equals 4 to infinity, the derivative's positive, so f is increasing. 4 to infinity. So f of x is increasing on these intervals. And the reason we know that is because the derivative is positive there. So I'm going to remind myself, I know this because f prime of x is positive. Now, where is f of x decreasing? It's decreasing on the intervals. Let's see, where's the derivative negative? Only on this interval, right? So only between x equals 0 and x equals 4. So this is the only place where f of x is decreasing, on the interval from 0 to 4. And I'll justify my answer. I'll say I know this because on the interval 0, 4, f prime of x is negative. And this is one of those things that we want to remember, and it's an easy association. F of x increasing, f prime positive. F of x decreasing, f prime negative. Increasing, positive, decreasing, negative. That's an easy thing to remember. Okay. We know where f of x is increasing and decreasing. We just don't know the relative maxes and mins. We remember that our critical numbers are 0 and 4. So I'll erase that. And I need to find maxes and mins. So we sketch a rough graph of f of x based on our knowledge of where f of x is increasing and where it's decreasing. And we're not going to use the x and y axes as our frames of reference. We're going to use the critical numbers, x equals 0, x equals 4. Here's x equals 0, And here's x equal 4. And from negative infinity to x equals 0, f of x is increasing. And an increasing function goes uphill. So here's f of x increasing. And between x equals 0 and x equals 4, f of x is decreasing. And a decreasing function goes downhill from left to right. And then from x equals 4 to infinity, f of x is increasing again. So the graph goes uphill, increasing. And to find our relative maxes and mins, we just look at the graph and find them by inspection. X equals 0. 0 f of 0, that's a relative max. And here at x equals 4, and f of 4, this is a relative min. And I'm obligated to compute the y coordinates of these things, if at all possible. So let me write this down. Relative max, 0, f of 0. If I take 0 and plug it in here, I get 0 minus 0 plus 1. So 0, 1 is a relative max. And relative min, x equals 4. Now to get a numerical value for this, I'm going to have to plug 4 in here. And do I know the 5th root of 4? I'm sure I don't. So what I'm going to do is just leave it as 4 to the 9/5 minus 9 4 to the 4/5 plus 1. That's the best I can do. I don't really like it in that form, but I don't know what the 5th root of 4 is. Very few people do. So let's see, x equals 4, and f of x equals 4 to the 9/5 minus 9 times 4 to the 4/5 plus 1. This is f of x, and this is the best that we can do. Now the value of this exercise was just to let us know that yes, there are such things as type B critical numbers. They do pop up in exercises, and they actually do pop up in practical applications too. But we ignored type B critical numbers in our first 2 examples, and I did not want anybody thinking that we've heard about type B critical numbers, but I guess they don't exist because we've never seen an example with type B critical numbers. Well, here's an example. And we'll get a few exercises to work on that are very much like this, just so that we can have practice finding type B critical numbers and then drawing the graphs of type B critical numbers, finding the relative maxes and mins. And getting good at this is just a matter of practice. And it doesn't take that much practice. We get a few exercises under our belt and we'll be good.